that Chapter 18 is turning out to be okay so far. After all, it is pretty straightforward stuff, addition of a nucleophile to the CO electrophile. But then you see random reagents like this and you say, maybe it's not as straightforward as it seems. Well, I tried to help you out understanding when you get two single bonds versus one double bond. Oh, and then sometimes you get an enamine instead of an imine. But the take-home message, as usual, is think mechanism and you will be fine. And I think that is really especially true when it comes to looking at the aldol. So, this is where we're at. We've looked at the addition of oxygen nucleophiles and nitrogen nucleophiles, and we threw in the Wolff-Kishner. Now we're going to look at addition of a carbon nucleophile. Well, we've already looked at addition of carbon nucleophiles. We looked at the addition of, Grignards and organolithiums in Chapter 17. But these are soft carbon nucleophiles in that we're now looking at addition of enolates. So this mini lecture will just focus on the introduction, a big overview, and then we'll look at some of the nuances in subsequent mini lectures. Well, what do I have to tell you? Well, the aldol reaction, same old electrophile, the CO of an aldehyde or ketone. And remember that aldehyde being more reactive, it's actually much more effective at doing aldol with an aldehyde. But nothing new under the sun here. That's my electrophile. Now, the new nucleophile? Well, it's an old nucleophile. We've been looking at the enolate electrophile since, last semester. No, it's just acid-base chemistry. We get to our enolate by the addition of base, which deprotonates the alpha hydrogen, like so. And that's certainly very much doable because it's delocalized and stabilized by resonance. So the pKa of the alpha hydrogen is not too shabby. Now the aldol reaction, we'll typically see it run in basic conditions because of that enolate, but it can be acid catalyzed. So just like most of the other reactions in Chapter 18, we can have acid or base catalyzed addition. So here is our prototypical example of an aldol reaction. And what you can see right away is, I only have one reagent and a base. Okay? So what you have to remember is that when I show this, I'm talking about how many moles, how many bazillion molecules of this particular molecule. Tons and tons and tons. So what's happening here is I'm going to generate the enolate of that aldehyde. So there's my nucleophile. Well, and it's in the presence of a whole bunch of undeprotonated aldehyde. So my nucleophile and my electrophile are basically coming from the same molecule. This is called a self-aldol. So let's look at this in some detail. Basically, there's my electrophile. Here's my nucleophile. When I react those two together, I get this guy. And what you can see is that can lose the elements of water right here, minus H2O, to dehydrate and give you a conjugated aldehyde. So the key huge hint and bells and whistles of the aldol are this 1,3 relationship between the carbonyl, the ald of the aldehyde, and the OH, the ol of the aldol. So just to make it really clear, here is molecule 1 of my starting aldehyde, and here is molecule 2. Both 5 carbon pieces. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And there is the bond that was made between the alpha hydrogen of the aldehyde and the carbonyl carbon of the same aldehyde. Under certain conditions, especially if heat is involved, you go ahead and get dehydration. So the other kind of bell and whistle for the aldol is that the target has the alpha beta unsaturated carbonyl. Well, and you can imagine we can use those in all kinds of reactions. So now we have really opened up our synthetic toolbox. Whenever I see a 1-3 relationship like this, what I'm going to think about is pushing that lone pair back in, breaking this bond, and kicking the lone pair right there to give me back 1, 2, 3, the aldehyde plus this enolate. So what you can see from this particular example is that this is another example of a self-aldol. 1, 2, 3, 4. Oh, no, it's not. We've got a 4 carbon piece here and a 3 carbon piece here, but it's an aldol nonetheless. So another example, when the molecule has already dehydrated, how do I disconnect it? Well, I just remember that that is an alkene, and alkene can come from dehydration. So I put my alcohol on carbon 3, this 1-3 relationship, and then what can I do? Well, push it back in, break the bond, and there you go. There is your aldol. Aldehyde plus enolate. And that gets you to your product. So, this should look real familiar, because it's basically the alcohol disconnection. In our alcohol disconnection, as you will remember, we pushed the lone pair of the oxygen back in, and maybe I kicked out a CH3 minus to give me that disconnection, addition of methyl lithium to benzaldehyde. Alternatively, I could kick out H minus. Okay, and again, this is not a mechanism. This is just thinking about how can I make this. If I do that, that's a reduction. I would add H minus to this skeleton, which happens to be acetophenone. Finally, my third possible alcohol disconnection would be something like this. Every time I push the lone pair from the oxygen back down to regenerate a CO double bond, in this case I'll kick out the phenyl group, phenyl lithium, phenyl grignard added to that 2 carbon aldehyde, and boom, all 3 of these are great ways to make that target molecule. But now, when the alcohol happens to have 1, 2, 3, a multiple bond of, say, a carbonyl or CN or something like that, 3 carbons over, guess what? You should think alcohol disconnection, because that means you can kick out an enolate. So I'm talking CH3COH plus CH2 minus that enolate. So just to check your answer, does this react with that to give this? You better believe it does. So the alcohol disconnection is your friend, absolutely. Think aldol whenever you see that 1-3 relationship. Now I gotta say there's one thing about the aldol that should be driving you crazy, and that is that I've always said you can't kick out OH minus. OH minus is a terrible leaving group. But guess what? I lied. I mean, basically that's what's going on right here. We have a base, our methoxide, that is pulling off that alpha hydrogen and kicking out OH minus. Oh, that's so ugly looking. Well, that's not exactly the right mechanism. The base is simply deprotonating that hydrogen to give you the enolate, which of course makes great mechanistic sense. So there's no problem there. So that's very easy and mechanistically sensible. But how come we can rationalize now that that anion can come down and kick out OH minus to take you to the alpha beta unsaturated carbonyl? Well, the reason we can say that that will happen is because it's extremely stable, the alpha beta unsaturated carbonyl. That's a thermodynamic sink. So if I'm going to try and do this, that is not going to happen. But if you have your anion adjacent to a carbonyl, in other words an enolate, happens in a heartbeat, no problem whatsoever, because that's a very stable product. All right, see problem 1825 to help you understand this a little better. So other points about the aldol, like I said, it works under acid catalysis as well. Remember that enols and enolates are formed under acid or basic conditions. Under acidic conditions, you have the enol, not the enolate. Ketones, they don't work so well. Okay, in fact, it's kind of a sterically crowded problem, so that to get an aldol to work with a ketone, you have to force the equilibrium one way or another. So, for example, here we go ahead and convert the alcohol in situ to the chloride to prevent the retro-aldol, that disconnection we were just looking at, from taking place. One thing for aldols with ketones is if you do the dehydration step, which again happens quite readily, and certainly if you add heat, then your product is actually quite favorable even if it is a ketone. Okie dokie, so what's up with this? Well, for this I have to do a little drawing here. And here's my so I worked at a sailboat rental place once, and we have to call out, say, boat number 99, your time is up, you need to come back in, or else I'm going to have to start charging you rental. But then one day this person said to me, my fellow coworker, Nancy, we don't have 99 boats. We only have 75. Oh. Boat 66. Boat 66. Are you in trouble? Yeah, that's supposed to be a tiller or something. Okay, that was a bit of a stretch, but that's our joke for the day, and that's our aldol introduction, and we will see you in class.